Hello everyone. In this session I am going to explain another, that is mechanical simple harmonic oscillator. So till now we studied the SHM, simple harmonic motion, and what are its characteristics and differential equation, and what is velocity, acceleration expressions, and time period, what is the time period for that simple harmonic. Similar to that, we are considering another mechanical simple harmonic oscillator. So that is a spring which is attached with the load. So then what are the forces which is acting on that, and what is the acceleration which it will execute with the acceleration, and what is the displacement we used to get it from that, and time period formula same to that only, that is mechanical simple harmonic oscillator. So a spring attached with the load. So now consider a spring. Consider a spring Consider a spring. One end is attached to the rigid supporter and the another end is freely falling. Okay. So that just it is in the form of helical structure, and when we used to attach it with the load, what will happen? So then the extension will be takes place and the restoring force will be act on that spring, that we know that. So now the same spring which is attached with the load, now the same spring which is attached with the load, so that we can consider that as mg. Then the linear restoring force acting on that. So what is the length, what is the displacement it will shows? So that is L. Now the initially the length of the spring is this much, then after attached with the load, then when the linear restoring force is acting on that spring, then the what is this length, the distance that we can represent it by as a small l. What is the displacement it will execute? So that is, then what is the restoring force acting on this spring, that is F is equal to minus KL. F is equal to minus KL, where K is the spring constant and L is the length, that is the displacement of the spring. So spring K, we know that force per unit displacement, how much it will shows the stiffness of the spring. So when this spring attain a equilibrium position, so then at the equilibrium position what will happen? At the equilibrium position, the linear restoring force and the force due to this weight will be balance each other. The two forces which is acting on this spring will get balances each other. Then what we will get? So that at equilibrium position, at equilibrium, when two forces balances each other, when two forces balances each other, then we will get therefore F plus mg is equal to 0. Okay. So one, that is the linear, one force is that is the linear restoring force, and the another that is force due to this weight. Then what we will get? Minus KL plus mg is equal to 0. So then if we take this outside, then KL is equal to mg. So K is equal to, we will get mg by L. Just name this as equation 1. This is at the equilibrium position. What is the spring constant we are getting? That is K is equal to mg by L. Next, if the same spring if we pull it down, still if we pull it downwards, then what is the displacement it will takes place. So that is, now we are going to represent it by one, the same spring which is attached with the rigid supporter, so now the what is the displacement it will takes place. So that displacement is represented by a y. So 1 with the same spring, if we pull it downwards, then what is the displacement it is showing. So that is, we are representing by the small y. So then here, what is that? The total forces acting on this spring, that is here F prime, that what we used to get, that is F prime is equal to, so already linear restoring force is there, that minus KL, and the restoring force that is due to this displacement, that we can represent as minus Ky. So now in this spring, the linear restoring force will become, that is F dash is equal to minus KL minus Ky, 1 which is actually the length of the spring which is attached with the mass. But when we used to pull down this same spring still downwards, then what is the force, the linear force which is executing, that is F dash is equal to minus KL minus Ky. So that's, therefore we can write that as, if we pull it downwards, the spring with the displacement y, then the force, then the linear restoring force acting on that spring is, then the linear restoring force, that is F prime, will be F dash is equal to minus KL minus KY. So this we can, here the minus K is common, so that take outside, then we can write this as minus K of L plus Y. So this we are getting here. But now what is the total force acting on this spring? So that if we take that, then we will get the expression. Now the total force acting on the spring, that we can represent it by force acting on the spring. The total force acting on the same spring, so that is Ft is equal to, one is due to the weight, that is mg, and the another mg plus F dash. So now simplify this, that is mg plus F dash we already have, that is directly we can write minus K of L plus Y. Then if we simplify this, now substitute the K value here, that is equation 1, by substituting equation 1, then what we will get? So, then mg is equal minus k in mg by L into L plus 1. Now open this bracket, then what we will get? Mg minus mg by L into L. So minus mg1 by L. So here L will get cancelled. So when the L will get cancelled and first term is in terms of positive mg and second term is in terms of minus mg. So then this also will get cancelled. So then what is the remaining term we are getting here? Minus mgy by L. So this is what is the total force acting on the spring. And this we know mg by L. What is mg by L is k value. So now write again in terms of that. From equation 1, we get Ft, that is total force acting on the spring, is equal to minus Ky. So now what is the total force acting on this spring, mechanical simple harmonic oscillator? So that is Ft is equal to minus K into Y. If the acceleration is set up in the spring, that is d square y by dt square, then what we used to get? So again take that, what is the total force acting on the spring? So that is Ft is equal to minus Ky and so Ft, so that is m into acceleration. So m into d square y by dt square from Newton's second law. Then we used to get minus Ky. Okay. So d square y by dt square, divide this equation by m, then we get minus K by m into y. So where this K by m, where K by m is equal to omega square, then this will become d square y by dt square is equal to minus omega square y. Okay. So now the acceleration, from this equation we can analyze that here the acceleration is directly proportional to the minus y. So then we know that, so in the simple harmonic motion, acceleration is always directed towards the mean position, whether the body is compressing or elongating. So that only now we prove. So if the acceleration is set up in this spring, means that acceleration is directly proportional to the displacement but in the opposite direction. This negative sign indicates that is in the acceleration is in the opposite direction to the displacement. Suppose the displacement is in positive, then the acceleration will be negative. So vice versa. Acceleration is directly proportional. Then for this same spring, what is the time period? So we know that what is the time period formula for simple harmonic oscillator. So that we studied in the last class. So that is T is equal to 2 pi by omega, or from initially 2 pi root of acceleration by displacement. Now we have to find out the time period formula for this. Then similarly what we used to get. So simple harmonic oscillator, that is attached with the mass m, then what is the time period formula? So time period from a simple harmonic oscillator, you know the time period for simple harmonic oscillator. So that is T is equal to 2 pi root of displacement by acceleration. So then what is the displacement here? So that is when pull down, so we know y, t is equal to 2 pi root of y divided by, and what is the acceleration? We are getting that acceleration d square y by dt square is equal to minus omega square y. So acceleration is equal to minus. So this negative sign, we can ignore this here, negative sign, ignore that negative. Then what is the acceleration? We get omega square y. Just generally, when we consider for the generally, then the acceleration is equal to omega square y. So what we get? Omega square y. So then y will get cancelled and 1 divided by omega square. But omega is nothing but what? Omega square is k by m. Omega square is equal to k by m. Then we will get t is equal to 2 pi root of m by k. So this is the time period formula for the simple harmonic oscillator, that is mechanical simple harmonic oscillator. So then what is the frequency? So reciprocal of that, t is equal to 1 by f. So time period formula, what we get? T is, once again write it, t is equal to 2 pi root of m by k. So then what is the relation between frequency and time period? We know that t is equal to 1 by f. So now we are going to find out the frequency. Therefore f is equal to 1 by 2 pi root of k by. So this is the frequency for the mechanical simple harmonic oscillator, that is when the spring is attached with the load. So this is about the simple harmonic oscillator, mechanical simple harmonic oscillator. So next is spring constant. So what is the spring constant? What it says, that spring constant. So if we consider any spring, one end is attached with the rigid supporter and the another end is which is attached with some loader. So this is in the form of electrical structure. What it says that, what is the value? Nothing but spring constant. So it says that how much the spring we can elongate or compress within the elastic limit. So the spring constant, it is defined as the magnitude of the force which is acting on a spring. Due to that, it will produce a unit extension or compression within the elastic limit. So force constant is defined as the force constant defined as the magnitude of the force which produces unit extension or compression within the elastic limit. Within the, so what it says that, so spring constant we know that force per unit displacement, right? So generally that negative sign, if we ignore that negative sign, whether it will be compress or expansion. So generally K is equal to force per unit displacement. From this, that is in terms of extension or compression within the elastic limit. So every spring having its own properties, that is the elastic limit. So that if the spring constant is more value, then it will be more stiffer. So suppose the spring constant of that value will be 12, then that spring having more stiffer. So suppose it is 6, then it having less stiffer. That means, so we used to observe this in the vehicles. So car and bike, how that spring constant, it's vary. So that's why if the larger value, if the larger spring constant value, then it will be more stiffer. So then what is the physical significance? It says that larger the spring constant, then larger the spring constant value, then it will be more stiffer. So if it is having a more spring constant value, then that spring is more stiffer. So it is very widely we can use in the automobile. And so totally it is the, what it says that it physical, how much we can elongate and compress the spring within the elastic limit. How much the spring can be stretched. How much the spring can be stretched within the elastic limit. So totally it is a measure of the stiffness of the spring. So this is about the definition and physical significance of the any spring if we consider. Then now by considering this spring, that if we take one more spring, then if we connect the springs one end to the another, that is in series, then what is the spring constant? And if we connect the spring parallel, then what is the spring constant? So that we have to find out now expression for the spring constant. So now we have to find out the derivation for the spring constant. Now first, springs are connected in series. So now first let us find out when the two springs are connected end to end, then what is the spring constant we used to get. Next, first now let us consider the two springs. Consider the two springs. Let us consider the two springs, so that is S1 and S2, which are connected end to end. And the spring 1 spring constant will be K1 and second spring constant will be K2 respectively. Okay. Then what is the forces which is acting on this spring, that is on spring S1, that is let it be F1, F is equal to minus Kx, and what is the displacement it's usually take, that we will do. Now that is generally 1. The forces will be here when we used to connect the two springs end to end, the forces which is acting on this spring will be same. That means this, when we used to apply still more weight, then that spring will be stretched with the same force. So that's why here the force will be same, the force acting on these two springs same in the case of when we used to connect the springs in series. If when the still more, if we add more weight, then what will happen? What is the displacement it used to take place? It will stretch. Okay. Let it be now the again if we are pulling downward with adding more weight, then what will happen? The displacement will take place in the spring. So what is that displacement? So if we can take the reference, then what is the displacement? It is elongating. So that displacement for spring 1 will be x1. And for spring is 1, what is the displacement? It is elongating, so that we can consider here. And for spring 2, what is the displacement? That will be x2 up to here. So what is the changes in the length? So this much of, then what is the total distance? So that is the total increase in the length of the spring when the two springs are connected end to end. So that is x. So now let S1 and S2 will be the two springs. So corresponding to that, so what is the spring constant? K1 and K2. So when these two springs will attain a equilibrium position, so that will be balances each other. So now if x is the total increase in the length of the two springs, then the total force acting on the spring, that is the total force acting on the spring can be represented by x is equal to x1 plus x2. So just name it as equation 1. Okay. So now when both the forces acting on the spring, so at the equilibrium position, the two forces will be balances each other. One is restoring force and the another one is forces due to this weight. So at that condition, at equilibrium position, at equilibrium the two forces will be balances each other. So for spring 1, that is S1, so what is the restoring force that we used to get? F plus mg is equal to 0 at equilibrium position, when the two forces will be balancing each other. F plus mg is equal to 0. And what is the restoring force? We know that is minus K1. So because the different springs having the different spring constant. S1 is having K1 and second spring S2 is having K2. So here K1 x1 plus mg is equal to 0. Then we will get keep in the terms of x1. So, that is K1 x1 is equal to mg. So, K1 is equal, x1 is equal to what we will get, mg by K1. So, name it this has 1. So, already named 1. So, name it has 2. So, similarly for spring 2, for spring 2, that is S2 for second spring, then what we will get, F plus mg is equal to 0 at equilibrium position same. But here what is the restoring force for the second spring? So, that is F is equal to minus K2 x2 plus mg is equal to 0. So, here also keep it in terms of x2. So, then we will get x2 is equal to mg by K2. So, this is equation number 3. Substitute this equation 2 and 3 in equation 1. Okay. So, there when the two springs are connected end to end, then what will be the equivalent, K equivalent, that we used to represent it by a K equivalent. So, when we used to consider for two springs, that we used to represent it by the combination of two springs, combination for two springs, combination of two springs. So, combination of two springs, if K equivalent will be the combination of two springs, then how we used to represent it, that by K equivalent. K equivalent, if K equivalent is equal to, if K equivalent is equal to mg by x. So, that's why x is equal to, what we will get, x is equal to mg by f K equivalent. So, that is when the number of springs are connected, so that is in the combination, series combination, then we used to represent it by, that is K equivalent. So, now substitute all these values in equation 1 by substituting. So, this name it as equation 4. Substituting equation 2, 3 and 4 in 1. So, then what we will get? So, that is we get, so what x is equal to, what is x is mg by K equivalent, mg by K equivalent, and equation 2. So, x1, that is mg by K1 plus mg by K2. Okay. So, now mg is common and take the that outside, then what we will get, 1 by K1 plus 1 by K2. Here mg by K equivalent. So, now mg will get cancelled. So, what is the equivalent combination we are getting, that is 1 by K equivalent. 1 by K equivalent is equal to 1 by K1 plus 1 by K2. So, this is the, so when the two springs are connected in series. So, then so 1 by K equivalent. So, what we get? So, if we simplify that, that is once again write it, 1 by K equivalent is equal to 1 by K1 plus 1 by K2. Okay. So, then from this if we simplify, then we will get K equivalent is equal to K1 into K2 divided by K1 plus K2. So, this is the K equivalent when the two springs are connected. So, suppose if the number of springs are connected end to end more than 2, then that how we used to represent it, that by 1 by K equivalent is equal to, if the number of springs are connected, that is 1 by K1 plus 1 by K2 plus 1 by K3, so on. So that is 1 by K, n number of springs. So when the n number of springs are connected, so that multi number of springs can be regarded as the single spring. So then what is the general formula? So then that when the number of springs are connected in series, then that number of springs can be regarded as the single spring, can be regarded as a, so that can be written as K series is equal to K1 into K2 divided by K1 plus K2. So this is the formula for the spring constant to find out the stiffness of the spring, that is K1 into K2 divided by K1 plus K2. So similarly, when the two springs are connected to parallel to each other, then what is the spring constant? What is the stiffness of that springs? So that we can find out. Now again, when the two springs are connected parallel to each other, so that is springs are in parallel. Now the springs are in parallel. So one end is which is attached with the rigid supporter. So the two springs are attached with the mass. Yeah. So that is, this is S1, S2 with the spring constant, with the different spring constant K1 and K2. So and what is the restoring force acting on this spring? That is when, and here when the two springs are connected parallel to each other, and what is the force acting on this? That is, the force will be same for both the spring. Means at a time that spring will be moved downwards. When the two forces, when the two springs are connected parallel to each other, here the forces will be different. The forces will be different. So that is, here F1 is equal to restoring force acting on this spring is minus K1, and the displacement will be same when you used to add still more weight, and what is the displacement will take place? So that will be, and what is the displacement that is taking place? That the total, the increase in the length of the spring, that is x. So this one x, and the spring 2 F2 is equal to minus K2 x. The total increase in the length of the spring is, that is x. So therefore this we can represent the total forces acting on the spring. The total force acting on the spring is F is equal to F1 plus F2, the total force. So that is, therefore we will get for spring 1, for spring is 1, so that is F1 is equal to minus K1x, and for spring 2, for spring S2, the forces will be F2 is equal to minus K2x. This with a different spring constant, but the displacement it will be the total, that will be same. What is the changes? So therefore if we substitute in the above equation, then what we will get? F is equal to minus K1x minus K2x. Then take the common outside, that is minus x of K1 plus K2. Okay. So when the two springs are considered, then what is the equivalent of that. So if we consider that is for general, that K equivalent, so LHS side, then we will get Kx, that is minus Kx common, K equivalent. If when we used to consider equivalent, K equivalent, that is equal to x into K1 plus K2. So x will get cancelled and the minus also will get cancelled. So what we are getting, K equivalent is equal to K1 plus K2. So, K equivalent. So then when the two parallel springs are connected, that is parallel to each other, then how we used to represent it, that is K parallel. If the number of springs are, multi-number of springs are connected, then K1 plus K2 plus K3, so that is so on. K, when the n number of springs are connected, that we used to see. Generally we can represent it by Kp is equal to K1 plus K2. So this will be the spring constant when the two springs are connected parallel to each other. It is Kp is equal to K1 plus K2.